Okay, so now we're going to do something that's also pretty weird. So you really got to concentrate to like make sure you're following along, because I'm going to start drawing like a weird diagram, and I'm going to be talking about these diagrams for like the next 50 minutes. And so if you like don't understand what's going on, you'll be a bit lost. Okay. So let's keep another example. For whatever reason now, we have this like 12-dimensional vector. So we have like 12 amplitudes. And rather than drawing them as like a height 12 vector, I'm going to kind of draw them in like the the cube notation we like often do, where, especially if there's like two qubits, we'll have like A going in one direction and B going the other direction, and we put like the 4 amplitudes in like a square. We're going to do a similar thing here, but where we have like a rectangle. So it's going to just be a different way to visually depict 12 numbers. Instead of stacking them all in a height 12 column, we're going to stack them in some kind of like more logical 2x6 rectangle. So this is going to be like our new way to draw 12-dimensional vectors. Okay, I'm really going to be using this like running example with L being 6 like a lot. You should always keep in the back of your mind that like, okay, in general this is like L, not 6, but it'll be nice to have a concrete example. So I'm going to draw it like this, and let me just draw it and then explain it. So I'm going to have like a bubble and a bubble. And this is going to be like the B direction. So this is going to be sort of the 0 and 1. Now, we're also going to have like an A1 through A5 direction. Now, normally when we drew these diagrams in the past, we'd have like a separate direction for each, a dimension for each of the qubits. And be like a 2 by 2 by 2 by 2 by 2 cube. But we're going to put like all the other dimensions like in a row. So let's draw this. We're going to have 6 of them. 2, 3, 4, 5, 6. 1, 2, 3, 4, 6. Okay, and just to like remind us of these like square or cube pictures, I'll put these lines in here, although they don't really mean anything. But I'll put them in anyway for fun. Okay, and the labels of these rows are like 0 and 1. I shouldn't put this here. And the labels of the 6 columns are like these labels from S. So this will be like the 0, 0, 0, 0, 1 column, 0, 0, 0, 1, 0 column, 0, 0, 1, 0, 0 column, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, and the last one is like 0, 1, 0, 1, 1. Okay. And now we might have 12 amplitudes in here. So like, I don't know, P, that's about chalk. Let's do P, Q, R, S, T, U, V, W, X, Y, Z. I thought what to write here. Omega? I guess it kind of looks like W, but whatever. Okay. So this is like 12 numbers, and so it's just like a different way to write a vector that has like 12 real numbers. We're going to write them in like this 2x6 picture. And this really stands for like this vector, P, Q, R, S, T, U, V, W, X, Y, Z, W, or Z omega. And like the entries here correspond to, like this is like 0, 0, 0, 0, 1 tensor. I should do this in black. 0, 0, 0, 0, 1 tensor 0. 0, 0, 0, 0, 1 tensor 1. 0, 0, 0, 1, 0 tensor 0. 0, 0, 0, 1, 0 tensor 1. Okay, all the way down, and the last one is 0, 1, 0, 1, 1. No, 0, 1, 0, whatever it is. Yeah, tensor 1. Okay, so what I'm saying, every state now that we're ever going to create for these qubits A1 through A5 and B will only have like 12 non-zero amplitudes, and there'll be amplitudes on like all the things that like look like S possibility here and like 0 or 1 over here. So it's like P amplitude on the first 5 qubits being 0, 0, 0, 1, and the B qubit being 0, Q amplitude on this, R amplitude on this, and so forth. There are 12 such possibilities, and we're going to like always arrange them into this 2 by 6 picture. And hopefully it makes sense, right? Like the S is like 0, 0, 0, 0, 1, 0, 1. Yeah, checks out. OK. Any questions yet? OK, so now to make sure that I'm following, or you're following, imagine we get to this state, and then we do R. Say from here we do R. What's the new picture? If we were to like redraw, like we get like a new 12 amplitude state, we would redraw it in like this diagram. What would it look like? Yeah.
Move everything one down the train track.
Yes, very good. You move each vertical pair like one step, yeah, down this like track. Exactly. Because R has the effect of just sort of cyclically shifting like this first 5 coordinates. So like R moves like this to this, and this to this, and this to this. And like the B part doesn't change. So like P would just go to here, R goes to here, T goes to here. And similarly, Q goes to here, S goes to here, and so forth. OK, so kind of weird, but that's what's going on. So let me even draw that. In this picture, like what happens is like this pair goes to here, this pair goes to here, this pair goes to here, and so forth. But it will be nicer to draw it like that. I should mention that like for the rest of the lecture, we're just going to be like doing math. Like there's no quantum computing content. It's just like a long math problem to like figure out the planes of rotation for this R. OK. So indeed, if we were to apply R, we get like a new picture. It looks like this. I won't put the labels in, but I don't know, I'll put this in. And indeed, we'll get like P, Q, R, S, T, U, V, W, X, Y, Z, omega. OK. So this represents how like this 12-dimensional vector changes. OK, now I got to make one more like wacky notational move, which is we're going to often start thinking of this as 6 consecutive column vectors of height 2. It's really, again, like we're saying, like we're going to focus on this 2D vector, this 2D vector, this 2D vector, this 2D vector, but now they're like in nice columns. And we're going to start writing, instead of, let's say, this 2D vector, 1, 0, I'm going to depict it like this. So I'll put the parentheses for like, I don't know, to indicate this is a 2D vector, but I'll just like draw it as though it were like a 2D vector. OK? Or for like this one, this is like 45 degrees. If I draw that, you know, instead of that's root a half, root a half. Or if I draw, I don't know, this one, that means 0 minus 1. OK? So I'm going to visually depict 2-dimensional vectors now. So therefore, finally, when I start talking about like a 12 amplitude state, I'll start like drawing it like, this. I don't know, this is like just a random example. And I'll be like, that's the state of the 12 qubits, like this picture. And like you'll be like, what? But first you remember like, okay, this is whatever it is, I don't know, 0.8, 0.6, and this is 0, 1, and whatever, -1, 0, blah, 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 blah. And that really means this, and that really means, those 12 numbers are arranged like this. But the point is, like, if this is your representation of like the 12 amplitudes of our state, and you apply R to it, it just like shifts these columns cyclically. It moves these different little vectors around in a cycle. OK, any questions about this? All right, let's pass this out so we don't forget as well. OK. So what are we doing, by the way? We're trying to find the planes of rotation for this operator R on 12-dimensional space that acts on 12-dimensional vectors by this like sort of cyclic shift. So what I'm going to give you now is tell you one vector which is in one of the planes of rotation. And like this is like the sort of like the most canonical, nicest vector in one of the planes of rotation. This vector is going to be in, so this R has planes of rotation that are like 1/6 of a circle, 2/6 of a circle, 3/6 of a circle, 4/6 of a circle, 5/6 of a circle, and 0/6 of a circle. That's what I've told you in advance. We're now trying to check that fact. I'm going to tell you one vector that's in the plane that rotates by 1/6 of a circle, which is 60 degrees. And yeah, so I'll now just tell you a vector that has this property. And I'll draw it like this. And this will be a very important vector. And it doesn't really have a name, but as we'll see, it acts very much like the EPR state, like the entangled, the EPR state was like an entangled state for 2 qubits, A and B. And it's going to be very similar to like a very interesting maximally entangled state for like these 2 blobs, the A qubits and the B qubit. And it's going to have exactly that same property that the EPR pair had. Remember the EPR pair had this property that like if you have 2 qubits and you get them into this EPR state, then like if Alice does like, let's say a rotation on her qubit, it's the same as if Bob did the opposite rotation on his qubit. And I even depicted this, I always depict this in my mind as like a steering wheel, where like Alice has her like left hand on the steering wheel, and like Bob has his right hand on the steering wheel, and if like Alice rotates, it's the same as the Bob rotated the other way. So because I have that mental picture, I'm going to call this 12-dimensional state a steering wheel state. So here it is. So this is going to be the state, so I'll call it SW for steering wheel, and I'll call it 60 degrees, sub 60 degrees, because as we'll eventually see, it's lying in the 2D plane of rotation that R rotates by 60 degrees. And here it is. So this is just like a definition. And I will say here that like I'm doing like a thing that's like a little bit annoying when like mathematicians do it, where they just like tell you the answer out of the blue, and then we'll just check that this answer is correct. So I'm not going to try anymore to like motivate like how we got this, but maybe when you see it, you'll be like, oh, I kind of see like why it has the property that it's getting rotated 60 degrees. But anyway, you'll just have to accept it. So I'm going to draw it in this fashion. So it's going to have these 6 columns. Uh-oh. Yeah, OK. Didn't space that too well. But anyway. OK, so here are the vectors. First one is horizontal. Next one is kind of down and to the right. And like this is 60 degrees. And then the next one is like down and to the left. This is also like 60 degrees here. And then the next one is like up and to the left. And then the next one is like, wait a minute. Hold on. Got it wrong already. Sorry, this one should be like this. OK, I'll draw it in a more clear way in a second. OK. The point is, these 6 vectors, let me just draw them on the circle here. It's a terrible circle. But the first one is like, this is number 1. And then you just go by 60 degrees. So this is number 2. This is number 3. Actually, I should call this 0, 1, 2, 3. Keep missing things. 60, 60, 60. This is 3, 4, 5. OK, it looks like a snowflake. Okay, imagine like this is a clock, and it's like, OK, this is like 3 o'clock, and then you go like 60 more degrees to this. You go 60 more degrees. This is like 9 o'clock. 60 more degrees. This is maybe 11 o'clock. I don't know. No. Anyway, you go 60 more degrees. You get here. 60 more degrees would take you back here. OK, so as I said, the angles of these vectors here are 0 degrees. I suppose this is negative 60 degrees. This is like negative 120 degrees. This is like negative 180 degrees, negative 240 degrees, and negative 300 degrees. OK, so if you were really to write this down as like a height 12 vector, like way back here, it'd be like cos 0, sine 0, cos negative 60, sine negative 60, cos negative 120, et cetera. This would be the steering wheel state. But we're just going to think of it as like, visually, where this like vector ticks around 60 degrees clockwise in each step. OK. And the point is, this is going to be one of the vectors that when you apply R to it over and over again, it somehow in this high-dimensional, 12-dimensional space like rotates by 60 degrees. And it's hard to visualize. But the first thing we'll understand is like what happens if you apply R to this state. Well, as we saw, it just cyclically bumps each of these vectors, 2-dimensional vectors, like one step down this railroad track, and the last one wraps around. So we get to, I'm having a hard time drawing this, but I'll do my best. This one, and then this one, this one, this one, this one, and this one. OK, so here, like this went to here, this went to here, this went to here, this went to here, and so forth. And what you notice is an equivalent description of how to get from here to here is if you just did a counterclockwise, like 60-degree rotation on each of the little columns. Like we 60-degree rotated this, counterclockwise, 60-degree rotated here, 60-degree rotated here, and so forth. So this is a sense in which it's like, it has this like steering wheel type property, which I'll now write, which is that if you somehow got yourself into this like amazing state, and then you applied R, it would have this sort of really simple effect of just kind of doing a 60-degree rotation on the B qubit. So this is like a fact. If you start A1 through, well, A5 in this case, and B in this very special state, analogous to the EPR state, SW 60 degrees, then let's see, applying R, by definition, this is the same as like applying, times 2 mod n to like a1 through a5. And maybe we'll like personify this a bit by like imagining that it's like Alice who does this. But as you can see, this is the same as though like a person called Bob were to just apply rot 60 degrees to B. And this is kind of pleasant, and this is why like this is such a cool state. It's because it's a very complicated state, and the algorithm is not going to like know how to get qubits into this cool state. But we're the mathematicians looking at this whole picture from the outside. We understand that like if you're in this cool state, then applying R has an extremely simple outcome. Applying R is literally just applying rot 60 degrees to this one qubit B. So this may make you feel, and you might even like have this intuition like, oh, we did it. Like we discovered like a vector with the property that like, oh, it's getting rotated 60 degrees by R, like every time you apply it. So you might be like, we did it, right? Like this is the vector that's in a 60-degree plane of rotation for R. That's true, but we didn't do it yet. We still actually have to do some math to like verify that that's the case. But hopefully maybe you're like moderately intuitively satisfied about that at this point. So just a plan for what's coming up. Like it's kind of like we discovered this vector, and I will show you later that indeed if you keep applying R to it, then it like stays in this two-dimensional plane, and every time you apply R, it gets rotated by 60 degrees. And of course, when you do it 6 times in a row, you get back to where you started. So it's 60-degree rotation. And then we'll do some more stuff. We'll find a perpendicular vector also in this plane of rotation that has the same property. And then we'll really be like, oh, great. We found like 2 spanning vectors for this 2D plane. We've really exactly found this plane of rotation of angle 60 degrees. And then I'll be like, oh, then we'll find one of angle 120 degrees, and one of angle 180 degrees, and one of 240 degrees, and one of 300 degrees, and one of 0 degrees. And that will be our planes of rotation of 0 over 6 tau, and 1 over 6 tau, and 2 over 6 tau, and so forth that we promised from the outset. And I should also say, like, before we get into it, like in general, like if L were like 10, then the steering wheel state would be like steering wheel sub 36 degrees, which is like 1/10 of a fuller circle, and there would be like 10 columns, and like here this would be horizontal, and they go by like 36 degrees, such that like when you do that 10 times, you would get back to where you started.